Adji from Columbia University. So she's a PhD student at Columbia. Sure, okay. So Adji is a PhD student at Columbia at the Applies lab, and she also works with John PhD. Her work is about problems at the intersection of graphical models and deep learning, and she's using it to improve sequence modeling in language. Prior to joining Columbia, she worked as a junior professional associate at the World Bank. She did her undergraduate training in France, and she holds a diploma engineer from Telecom Paris Tech, and spent the third year at Cornell earning a master's in statistics. And she's going to talk about deep sequence models.
Thanks, Rajashi, for the introduction. Hi, everyone. Thanks for coming. I'll be speaking today about deep sequence models, more specifically about two aspects of it, about research I've done on how to represent context and how to regularize these types of models. And I'll be discussing all of this in the context of language modeling. First of all, deep sequence models, like their name say, are models for sequences. And I like to think that all data are born sequential. You can look at even data that might not look sequential as a sequential data, like images, for example. You can look at them as a sequence of pixels. Here I'm showing typical sequential data, such as in finance, which you have on the left. That's the S&P index. Then you have speech, which is sequence of waves, and you have text data, which is typically a sequence of words. And then you have medical data on the right, which is basically recording a patient's visit at the hospital. And during each visit, you have different covariates. So why do we need to model these types of data? Because we want to help in decision making. You want, for example, to trade, and for that you need to be able to have a model of the past price for the stock. And we also want to model this data because we are somehow interested in generating more of it to help in supervised models. We want also to model this data to be able to do prediction and forecasting, and simply to do science. Now the question is, how do we go about modeling these data? And the complexity in doing that comes in the fact that there's a lot of dependencies that you need to take into account. There's dimensionality that you need to take into account. These data are very high dimensional usually. And there's also seasonality, meaning there are these trends in the data that comes every period for some of these data sets. And yeah, there's too many things to take into account, and it can be very complicated. But one family of models that has emerged as very good models for these sequential data is the recurrent neural network family of models. And they have been used in different settings and different applications, some of them being highlighted here, such as image generation. You have on the top left an example of the draw model, which is deep recurrent attention writer that basically uses a recurrent neural networks and samples a latent variable, passes this through a recurrent neural network, and use that hidden state to update some canvas and do generation. That's how they generate, for example, images or house numbers on the top right. Another success of RNNs is in generating handwriting or text in general. And on the bottom left here, you see the word under that's been drawn from a trained recurrent neural network. This is from Alex Graves' paper in 2013. Another success is in neural machine translation, where you basically chain two recurrent neural networks together. One encodes your, let's say you have a conversation, so you have a response and you have a query and an answer. Then the first recurrent neural network encodes your query, and the second one tries to generate an answer. And this has been very successful in machine translation. See, for example, a reference paper, Surskiva and al. in 2014. So these are all works that have showcased the capabilities of RNNs. And let me first say briefly what an RNN is. It's a neural network-based model. So you have an input X that's passed through a lower dimensional space, S, that is low dimensional. It's called the hidden state. And S conditions on the input X and the passed value of the hidden state S to output some value O, using matrices U, V, W for convention. And you can think of this architecture as actually a giant feed-forward neural network. That would be the graph on the right, where you stack feed-forward neural network across time. That's called unfolding the recurrent neural network. And what you can see here is that the hidden state, for example, at times t, can be written as some parametric function of the input word xt and the previous hidden state st minus 1. That's, I will call from now on, the transition function. Any recurrent neural network implements its own transition function. So you will have the simple recurrent neural network that will just take sigmoid of the linear combination of the input and the hidden state. And you will have the LSTM and the GRU that are different, that use gated mechanisms to compute their hidden state. That hidden state in the unrolled version can be seen as composing a function over and over. And that composition is possible because the weights are shared across time steps. So it's the same parametric function. And you are doing recursion. So that's why recurrent neural networks are very successful, because they use recursion and parameter sharing to share statistical strengths between your inputs at different time steps. Now, in language modeling, the output is usually a softmax that conditions on the hidden state at each time step. But it can be anything else. If it's real data, there will be no function mapped to the linear combination of the hidden state. So the output here depends on the type of your data. This looks very simple and very interesting, but one issue is that when you compute the gradient of the hidden state, because you are unfolding this recurrent neural network across many time steps, then your matrix W will end up being multiplied over and over up to the number of times you have unrolled the recurrent neural network. And if that number of time steps, let's call it big T, is very big, then you will run into exploding and vanishing gradients. Exploding if the matrix has a spectrum such that the lowest eigenvalue is less than 1 or greater than 1. So that's a problem, and that's why usually what people do is that they truncate the recurrent neural network. They unfold it not to for many time steps, but usually like 35 time steps or 50 maximum. So they are not benefiting from everything they can benefit from theoretically. Because if you look at this equation theoretically, you can capture all the dependencies in the sequence because there's recurrence. So that's a problem. Another problem is that your output matrix for certain data can be very high dimensional. For example, in language modeling, V is the size of the vocabulary, and depending on your data set, this can be very big. And what that causes is you end up with a model that has very high capacity, so you tend to memorize the data. That's called overfitting. I'll come to that problem later. Another problem is that the hidden state is low dimensional. So like say 1,000 hidden units. A hidden unit is a component of the hidden state. You have 1,000 of them, and you are supposed, the RNN's hidden state is trying to capture all the semantics and syntactic information into these 1,000 coordinates for all the data sets in your training data, for all the inputs in your training data. And that's just too hard to do. So that's what I'm saying here. The RNN is trying to do too many things. It's trying to output the right value at each time step, and it's also trying to encode past information. So the first problem that I'm going to talk about is the long-term dependency problem, where you run into this vanishing exploding gradient issue, and that prevents you from encoding all the dependencies. And that has to do with the way context is represented in recurrent neural networks. What I'm going to discuss now is what do we mean by context, in the context of recurrent neural networks. Let's read this passage from during the past campaign, US presidential campaign. If I read this, it says the US presidential race is not only drawing attention and controversy in the United States, it is being closely watched across the globe. But what does the rest of the world think about a campaign that has already thrown up one surprise after another? CNN asked 10 journalists for their take on the race so far and what their country might be hoping for in America's next. The goal is to predict the next word. Can someone guess which one it is? President, yes. President, commander-in-chief, anything that has to do with lead of the country. So one component of you being able to predict that is that you know that that's a word, that's a noun that comes after next, given the local syntax, which is America's next. It has to be a noun, according to English's rule. And so that defines the syntax. That's the context, but it is a local context. So you only account for few preceding words of the current word you want to predict. And in that case, order matters because it's the syntax. And there's a different type of context, which is global context. And that has to do with the theme in the whole document. So knowing that you have to predict the president has to do with you knowing that this text, this small paragraph is dealing with presidential campaign, country, things like that. And what we notice here is that the global context doesn't care about word order. So word order doesn't matter, unlike for the syntactic part where it mattered. Also, you have to account for the whole document within which the word you want to predict comes from. So there are these two. There's the local context, which defines syntax, and there's the global context, which defines semantic. How do we combine both? How do we have a model that can take advantage of both types of context? So one argument is that topic models are good semantic models. So I'm going to review briefly what a topic model is. These are generative models for documents. So let's say you have a bunch of documents, it's called a corpus. And for each of those documents, you posit that they have been generated by first having a list of distributions over the words. Each of those distributions is called a topic. Those are the colored boxes on the left. Then, given your document, you generate each word by first generating the topic proportion, so the amount with which the document deals with each of those topics. And from those topic proportions, which is the histogram on the right side there, you draw a topic assignment for each of the words in the document. So you will say, okay, for this first word, cold, let me draw that from this topic. Once you have that, once you have the topic assignment, you generate the word from the topic, because the topic, remember, is a distribution over words. So that's how the document came about. But the truth is that we don't observe any of that. We don't observe the topics. We don't observe the topic proportions for each document. We don't observe the topic assignments for each word. All we observe is that we have all these documents lined up, and we want to somehow discover these in an unsupervised way. And that's what the topic model gives you. One famous instance of a topic model is latent Dirichlet allocation. What it does there is it represents the topic proportion as, which is theta d here, as a Dirichlet with parameter alpha. The Dirichlet is a distribution over the syntax, over the simplex. So all the components of your vector theta d have to be non-negative, and they have to sum to 1. And the next part of the LDA model is the beta k, which is the case topic. It also comes from a Dirichlet with parameter eta. That's the box on the right there. Now, once you have the topic proportion, you can generate for each word, which is the inner plate. For each word n in the DS document, you generate a topic assignment ZDN from a multinomial, whose probability vector is given by the topic proportion. And finally, once you have this topic assignment ZDN and you have your topic matrix, you can generate a word from a multinomial that is indexed by the ZDN's topic. So this is the model, LDA model, and it has been very effective in clustering documents that deal with the same topics, discovering these topics in an unsupervised way. We don't say what those topics are. This is all from the model. So it's very cool. And the idea now is that, okay, you have that family of model, topic model that are known for being able to capture global properties of documents given by the topics, and you have the RNN, that's a sequence model that takes order into account. So you can combine them. You have the two things that you want. The topic model, I forgot to say, they don't care about word order. Usually they represent the document as a bag of words. So you take the document, you count the number of times each word in the document appears in it, and you record that number. So the document is a vector of counts. So they don't take into account order, and they also don't take into account stop words because they don't care about syntax. They just care about semantics. I will define stop words. It's a word that's there just to make the syntax correct, like the, about, with, those kind of words. So yeah, I have my semantic model, I have my syntax model. How can I combine them? The intuition in wanting to do that is you want the RNN to focus on capturing local dependencies. Remember, I motivated at the beginning that the RNN is just trying to do too many things. One of those things was capturing these local correlation, but also trying to remember the past. So we will instead just let it focus on capturing local correlation and have the topic model capture the global dependencies. So I'll have my RNN be my syntax model, and I'll have my topic model be my semantic model, and I'll combine them to make prediction. So how do we combine them? There's been a lot of work on it, but in topic RNN, what we do is we have the hidden states of the RNN that are the H's here, H1 to H6. My inputs are X1 through X6, and the outputs are Y1 through Y6. And for each of those input-output pairs, I compute my hidden state for the RNN, and I let the RNN decide whether the next word to predict should be a stop word or not. A non-stop word is a content word, so predict a stop word or a content word. I think I said, okay, so here the blue dots are the content words, so these are words that have semantic meaning. And when the RNN decides that it needs to output a content word, then in predicting the output Y1, I need to condition also on some latent vector theta. That's the topic. I'll come to it later. And if it has to predict a stop word, because that is just a syntax word, I don't care about conditioning on semantic meaning. So I don't condition on theta there. So that's what you have here. At each time step, I decide whether I'll predict a stop word or a content word. And depending on whether I output a content word or a stop word, I'll condition on the latent vector. So it's the same thing as the RNN. The hidden state HT is some parametric function of the input and the past hidden state. So that will give me the syntax, and I'll draw I'll call it stop word indicator, LT, at time step t, from a Bernoulli whose probability depends on the hidden state at time t. And now I'll do my prediction for YT as a softmax. Again, this is for language modeling. That has two components in its argument. The part that is coming from the recurrent neural networks, which is the V transpose HT, and the part that is coming from the topics, which is the B transpose theta. 1 minus LT when LT is 1, meaning it's a stop word, that term disappears. So it all makes sense and it's intuitive, but how do we learn the latent vector theta? So that's the part where we have to do inference, and what we do there is to have everything differentiable and jointly trainable. I don't know if that's the correct phrase, but I use neural topic models instead. So what I do is that I mimic topic models. So I'll represent my document as a bag of words, so a sparse vector of counts, and I pass that through a multilayer perceptron, so feed-forward neural network, and given the output of that feed-forward neural network, I sample a Gaussian from whose mean and covariance are from that feed-forward neural network, and I squash that through some function g that pose constraints or not on the vector theta. And once I have my that's called the variational distribution posterior. It's an approximate posterior. Once I have that and I have a prior on theta, I can use variational inference. The reason why we cannot maximize, I didn't say this, but the only observed variables here are the output y and the stop word indicator. Those were observed because the stop word is, there's standard list that define what a stop word is, like about, with, so you have that from the internet. And given that, I need to train the whole network, the whole architecture in such a way that the likelihood of the YLT pairs is maximized. But that likelihood is intractable because you have to integrate out the latent vector theta. So you won't be able to calculate it, so you won't have a clear objective. What we use instead is variational inference, which maximizes a lower bound of that log likelihood. It's called the evidence lower bound here, elbow, and it has this expression. It has two components. One, that's usually the recognition error, and the second one is some penalty that forces your distribution over theta to be a little bit spread out. So that's my objective, and I can use, if you're not familiar with variational inference, you can usually, the way you go from here is you approximate your expectation with Monte Carlo, and you can take gradient steps with noisy gradient steps with this objective. So vanilla SGDs should do, or Adam, or any other stochastic gradient algorithm. So yeah, that was topic RNN, and it has since been extended to, for example, conversation modeling, where you need to account for persona, for example. You can use that as your context vector. Remember, I use topics, but it can be anything. You can condition on anything that gives you some more information, so as to ease the RNN's work, if I can say. And another extension of this is by using a mixture of experts. So it's the same principle. Have on the left box, you have your neural topic model, and on the right there, you have your recurrent neural network that conditions on it. And the box in the middle is the topic proportions for the document. So it's the same principle, but the models are different. They use a mixture of expert, and we use just a plain softmax with the topic as bias. Yeah.
So does the gradient flow through the sampling process? So
Yes. Yes, it flows through everything because theta is continuous. The LT is observed, even though it's Bernoulli, it's observed, so it's not a, yeah. Yeah, everything is trainable end to end.
it's end to end.
Yeah. Actually, there was a previous approach that had the same intuition of using topic features with RNNs, that from Mikolov, 2010-12. And what he did there was he pre-trained the LDA model before, and then used the topic matrix to compute the word biases. So our approach was that, okay, we need to, first of all, be able to train the whole thing so that the RNN gets to decide which topics it wants to use or not. And also, we have to deal with the stop words somehow, because the topic models, they don't deal with stop words. They discard it, but we need that for the syntax model so that everything makes sense. And I didn't say that, but the way we, I said it, the way we deal with the stop word was not done previously. And in the extension, it's not done also, but I think that it's very important, because if you don't have this separation of what's my topic and what's my syntactic part, then there's an issue. And the way we deal with that here is via binary classification. So you have this clear delimitation of when to use the topic vector or not. So we tested this on next word prediction on the Pentry bank. And what I'm outputting here is 3 tables, each one corresponding with a different network capacity. So like 10 neurons. So your H vector has dimension 10, and 100 neurons dimension 100, and 300 neurons dimension 300. And the first row corresponds to the result from the plain RNN that doesn't condition on anything. And the second row is the baseline from Mikolov, which pre-trains the LDA and then uses that in the RNN. And the 3 final rows is from the topic RNN model using different recurrent neural cells. So we use the plain RNN, the LSTM, and the GRU, the 3 main cells that exist. And what we can learn from these 3 tables is that, first of all, adding these topic features always helps, and significantly. There, for example, in the first step, you go from 225 to 187.4. So that's significant. And the second thing we notice is that doing the joint training and taking care of the stop word the way we did helps even more. Because if you compare the second line with all the 3 other lines, you get always significantly better results. Yeah, so this is promising. What we also looked at is, okay, since we are computing these embeddings of documents, you can see the vector theta as being an embedding of the document. What would that look like? Does that actually look like topics or things that indicate that different documents are being treated differently? So I'm outputting here 3 documents, document embeddings. And okay, I couldn't put the text for all those 3 documents, but these were 3 documents. And you can see that certain dimensions of the vector theta are being picked up depending on which document I use. So that's also indicative that the model is doing something. We don't know yet, but let's see. This is a list of topics. The tags for 3 data sets, so you have AP News, IMDb, BNC. The tags are manually put there. It's not an output of the model. But if you read each column, you will actually want to put those names, because they come very, the words, the 5 words become they're very related into a common theme. So those are the topics. So you have this neural topic model that will give you things like this, and you have your document distributions. That's also some evidence. You have perplexity that gives you another evidence that this is a useful thing to do. And what we did further was that we tried to actually do this on another task, which is document classification. So you have the IMDb data set that has some of the documents that are labeled 0, 1, negative, positive, sentiment. And some of them, half of it actually, that's unlabeled. And we wanted to have an unsupervised way of building features from this data, and then use these features to do classification of sentiment. So what I'm showing you here in green and red dots is the positive and negative sentiment classified from all the IMDb data set. Actually, not all, from, I think this is 20,000 documents. But the separation is very clear. And the way we did this was that we trained topic RNN on the IMDb data, the unsupervised, the ones that didn't have the label. We didn't use the labels at all. So it's fully unsupervised. And at the end, what we did was we concatenated the topic vector, theta, and the last hidden state of the RNN. And that constituted one big vector. That's my feature for that document. And I map this into two-dimensional via PCA, and then I do k-means, and that's what I'm showing here. So it's telling you that, yeah.
How do you get the RNN feature from a document? Like, you have to back it.
Huh?
To get the features of the document from the RNN,
Yeah.
you have to pull it, because there are hidden representations for each word.
Yes.
So how do you form one vector?
I picked the last one.
Oh, you took the last one.
Yeah, I picked the last one. But that's an interesting question, because you can ask then, okay, are there other ways to actually computing the RNN feature? Yeah, the feature from the RNN, yeah. You can do attention. That's something I thought about, yeah. You can do attention, because the last hidden state might not actually, like we think it might not, the long-term dependency problem, it might not account for everything. And another question is that we attempted actually using only the topic part, because initially I thought that was the important thing. So I used only theta as feature. I didn't get anything that looked like this, and the error rate was very bad. But when you actually have the two components of the model jointly together, then you see a nice clustering. And that corresponds to an error rate, classification error rate 6.28%. That's very good for the IMDb. At some point, like for 2 days, I think we had state of the art. And then, and then there was the virtual adversarial paper that came out. That was 5.91. But they used, to be fair, they used semi-supervised. So that's why I bolded both of us. Yeah. So if there's no further question, I'll switch gears to yeah.
How did you choose the number of topics, and how did that affect you?
Yes, that's a great question. For this one, for 10, if I remember, I chose 10 topics, and then 300, I used 100 topics. So the number of topics, what I noticed was that the higher you keep it, you get better performance depending on your number of, it scales with the number of hidden states. But if you keep it too high, then you will lack interpretability. Yeah.
So did you evaluate all
Coherence, for example, I did not. They did though. They reported this paper. They reported numbers for topic RNN, but I didn't put it here. It was very similar in terms of performance. Yeah. Yeah, exactly. Yeah, it's like in LDA, you have to choose the number of topics. But the usual range, I think, is like more than 200 is like problematic or something like that. Yeah. Yeah.
So if you look at the generative story, right, so you have to pick from the K topics, you have to pick one topic, and then you have to pick one word, right? So
you mean here?
So this is LEA, but like the next figure. Yeah, this one.
Yeah.
So the theta are the topic parameters.
Yes.
And so there are K of them, right?
Yes.
So you have to sample.
It's one vector that's k-dimensional.
Yeah.
Yeah.
Yeah, but you sample K, and then from that K, there is a multinomial categorical distribution of that topic, and then you sample a word, right?
That would be for LDA, but for the neural topic model, there's no multinomial. It's integrated out. The Z here, yeah, it's integrated out.
Right.
So it doesn't intervene in the neural topic model anymore. All you have basically is is this part, theta D. The beta now is the B matrix. It's not latent anymore here. It's a parameter here. It was latent in LDA, but it's not anymore. And the word would be, yeah, it would be a multinomial, except that now we just use beta theta as a long vector of size, the vocabulary size.
So I guess my question is, there is no hard sampling, right? Everything can be like integrated.
Yeah, exactly. Yeah, there's no hard sampling. Yeah. Like LT is observed.
Mm-hmm.
Yeah.
Because you can tag something in something.
Yeah, exactly. So I'll switch gears to regularization. One problem that I mentioned at the beginning is that these deep sequence models are very prone to overfitting because they have high capacity. And there's this code from Hinton that I like a lot because I feel like it's very intuitive. It says, when a neural network overfits badly during training, its hidden states depend very heavily on each other. So remember, the RNN is like you have your input layer, then you have a stack of hidden state, and then you use those hidden states to have your output. What he's saying is that when it's overfitting, then those hidden states across layers and across time steps are very codependent. That's usually called co-adaptation. And we intuitively don't want that to happen if we want to avoid overfitting. So one natural thing to think about is, okay, inject noise into the hidden layers. So in the top figure there, you have a 2-layer recurrent neural network with 3 time steps that I'm showing here. And at the first layer and the second layer, I'm injecting noise at each time step. The noise at each time step can be the same if you don't want to mess too much with the dynamics of the recurrent neural network. But it's fundamental that you keep the noise different across layers, because otherwise what you're doing is you're just rescaling your whole hidden state. So you do that. I call this a noise injected RNN, and what you get is a nice regularization effect from the figure below. The black curves correspond to the RNN, and the yellow curves correspond to the RNN with noise injected in the hidden states, as I just described. And what we can see is that for the black curve, for the RNN, the training perplexity, this is perplexity per iteration, the training perplexity goes down. See the black one with the dots, but the validation perplexity starts going up after only 5 epochs. That's typical overfitting. But on the other hand, if you look at the RNN with noise injected, both of the perplexities keep going down, the perplexity on the training data and on the validation data. So this is promising. And what we did was formalize it even more. So if you want to inject noise in an RNN, I'll define that as a noise injected RNN. What you do is you sample, if you have an RNN with T unrolled with T time steps, you sample T latent variables, noise variables epsilon from some distribution with mean mu and spread gamma. This can be, the spread can be like the variance for the Gaussian or the scale parameter for the gamma, things like that. Once you have those noise variables, you compute your hidden state at time step t as a parametric function that takes the input xt, the previous hidden state zt minus 1, and now the noise variable epsilon. So see, the only difference with the RNN is that you're taking this epsilon as an additional input. Once you have that noisy hidden state, you now compute your likelihood by conditioning only on that, the same way you were doing with the RNN. So the likelihood is usually an exponential family, which accounts for all the data types we have in the literature: binary data, count data, real data, categorical data. And like I said, the only requirement for the noise is that, you know, it has to be chosen wisely, different across layers, not necessarily across time steps. And one example of of a noise-injected RNN is a dropout RNN. Dropout basically samples noise variables that are from a Bernoulli distribution. So these are binary noise variables, 0 or 1. And this is dropout for the LSTM. So these are the LSTM update, with the difference that now I'm multiplying the input xt with epsilon. I'm multiplying also the past hidden state with epsilon, and I do that for all the gates. The gates here are ft, it, ot. And I also multiply it with the part where I'm updating the cell state with the tan h nonlinearity there. So I'm adding these noise variables in the hidden state of the LSTM, but I'm doing so inside the gates and not outside. And what you get is something. I'll just speak about the dropout example for now and then move on to defining a desideratum for injecting noise into the hidden states of the RNN. What we want is that if we have an LSTM, we like LSTMs because they do great, they're amazing, but they overfit somehow. We want to benefit from everything they can do great while regularizing them. So we want to inject noise such that the LSTM is preserved in expectation. We want to do it such that if you draw the noise to 0, the noise variables to 0, then you still have the LSTM. And that condition, we call it the unbiasedness condition. It's as expectation under the conditional distribution of your hidden state, given the past hidden state of your noisy hidden state is the underlying parametric function for defining the LSTM. So if you do that for the dropout, it doesn't satisfy that condition. So dropout somehow doesn't recover in expectation the LSTM. So that's one difference from what we are doing here. And so the natural question that arises is how do we do this? How do we do noise injection in such a way that the underlying recurrent neural network is preserved? And two choices of noise regimes that allow you to do that is additive noise and multiplicative noise as defined here. So your GW, your parametric function that defines your noise hidden state is the sum of your noise variable epsilon t and the underlying parametric function for the parametric function for the underlying RNN. And for multiplicative noise, you have the same thing, but you're multiplying. Here, epsilon has mean 0. So when you're multiplying, the expectation respects that unbiasedness condition. And the way we now train this noisy LSTM, noisy RNN, noisy GRU is by maximizing the log likelihood, the marginal log likelihood, the one that corresponds to integrating out all the noise. So that's why it comes in expectation like that. And we also show that this is actually a bound on what you truly want to maximize. So that's a good thing. It's a lower bound by Jensen's inequality. And it's a sum across all time steps of per time step loss functions. And these are expectation over the noise of your log likelihood that conditions on the noisy hidden state. So the objective is clear, the condition is clear, and the architecture is clear. So what I'm going to do now is mention two connections of this method, two existing methods. The loss function is as shown above, sum across time step of the expected log likelihood. And you can think of this as doing some form of ensembling. So it's like at each time step, fixed t, you are actually averaging the predictions of many RNNs. Infinitely many, because the distribution on epsilon is continuous for the continuous case, because you can take epsilon to be Bernoulli. But you are basically averaging the predictions of many RNNs at each time step, and that's ensembling. you can say, okay, then, but you are not doing that in practice. In practice, we only use one sample of noise. But remember, the RNN has shared parameters. So at each time step, you train one RNN, and then the next time step, you have the same weights, but it's now at a better initial condition than the previous one, etc. So yeah, you can train it easier than when you train ensemble methods, but it still has that interpretation because of the expectation. And another interesting connection is empirical Bayes. The noise variables, they induce priors on the hidden states, and those priors are parametric. They come with unknown weights. And when we are maximizing the objective there, the expected log likelihood, we are implicitly learning the prior on the hidden states. And that's what empirical Bayes stands for. You learn the prior and use that in your, you learn the weights of the prior and use that to do inference. So there's that connection too. And you might say, okay, does this work? It actually does. It's very simple, but it improves on existing RNN models. For example, here I'm showing perplexity numbers, so the lower the better, for different noise distributions and for different models. The first set of numbers correspond to plain LSTM with these noise variables, and the second one corresponds to the dropout LSTM with these noise variables. The dropout LSTM is the LSTM with dropout applied to it. I'm considering that as a model and I'm applying the noise to it. And what I'm seeing is that for every of these distributions, I'm doing better than when there's no regularization, but also I'm doing better than dropout. So across tables, you have improvements, and you have improvements also within tables. Yeah. Mm-hmm. This is not this. There's the dropout. The basic dropout has problems with LSM, but it has been adapted to RNNs. This is recurrent dropout. Yeah. But yeah, I agree with what you say. Like, yeah, dropouts have problems with recurrent neural networks, but there is recurrent dropout that actually adds it to the recurrent layer. Yeah, so that's what we have here. And another thing that was interesting here, gamma is the scale of each of those distributions. It needs to be free because you need to be able to control the regularization level. But the problem is that there are some of these distributions like Bernoulli and beta that have bounded variance. So you cannot afford as much regularization as you want, depending on your data. So what we do to counter that is we rescale the noise. So you take epsilon follows a beta distribution with certain parameter alpha, gamma. What we do is we rescale, we find another random variable that is a function of epsilon, such that the variance of the random variable is unbounded. So the only concept is non-negative because it's variance, but nothing else. So the gamma parameter corresponds to that, to the rescaled noise. And one finding that we made was that the only parameter of the noise, the only characteristic of the noise that matters is that variance, is the spread of the distribution. The mean or the higher moments didn't matter. The mean, because we are using additive noise and multiplicative noise, was set to 0, so that was fixed. Another thing is that for the LSTM on language modeling, multiplicative noise always performed way better than additive noise. Additive noise performed worse than any number in this table. So that's something to look into. So I didn't report those numbers, but multiplicative noise is what you want for LSTMs. I report the same thing, perplexity, but for a different data set, just to see that we are not creating a method that's specific to the Pentry bank. So this is an alternative benchmark to the Pentry bank called the Wikitext2, and I'm reporting the same thing. I'm reporting the value of the spread, I'm reporting the distribution, and I'm reporting this on the LSTM and the dropout LSTM. And we see the same trend, that it improves on adding noise in the way I mentioned in this talk, is improving the underlying RNN model. So let me just summarize what we have learned so far. We have learned that, okay, RNNs have a lot of issues, but they're great. They have a lot of issues, but the two main ones are in long-term dependencies, which has to do with context, and they also overfit, so we need to regularize them. As far as context comes, what we need to do is that we need to combine a syntax model and a semantic model. The RNN being the syntax model, your semantic model, you are free to choose whatever you want. But I've shown results on topic models that show that they are, and across different works, people have worked on this, that topic models are very effective at representing semantics. And so the topic RNN is one deep generative model that uses that principle. Regularization is also important, and we saw that simply adding noise into the hidden states in an unbiased way, meaning such that the underlying RNN is preserved, is also very effective and always improves the capabilities, the generalization capabilities of the underlying RNN model. And we have a paper on that where we do that, that's called noising, which is very simple. But there are still some challenges that I'm currently thinking about. Scalability. There's a lot of work on scaling RNNs for language model, because remember, for language model, the output is a softmax that scales with the vocabulary size. So there's been works on scaling that, but I'm still thinking about it. So how do we make it more efficient and principled? And also one other thing is that I'm thinking about is how can we incorporate prior knowledge into these sequence models. For language, for example, there's a lot of things we know about language. We know that there's hierarchy in a document. We know that that, for example, when you reverse the letters in a word, the word still, you can still recognize that this is this word. So there's all these amazing things that we know about language that we somehow are not capable of encoding into meaningful priors. So I'm thinking about that too. And one final thing is improving generation, because right now it really sucks. Like, we cannot generate meaningful text with recurrent neural networks. Also, it's been making some progress, but it's still slow. I haven't seen a result where it was like, wow, oh, that came from an RNN in an unsupervised way. That's amazing. We are not there yet. And so, yeah, that's a big part of improving RNNs, is in looking into how to make generation better. And that might involve looking into different architectures, or looking into the objective, or looking into, I don't know, conditioning on different size information, things like that. Yeah, so this is it. Thanks for your questions. If you have any more, I'd be glad to answer.
Mm-hmm. It's drawn from a Gaussian, right?
Mm-hmm. Oh, here?
It's like a per document thing that comes from Gaussian.
Yeah.
If you instead, so could you use some other distribution, like a gamma, to ensure that like every topic has a positive?
You can do that, or what you can do is just put G instead of being identity, like we have in topic RNN, have it. That's problematic, actually. You have to set it non-negative, or you have to constrain the matrix B as non-negative. Yeah, so that you don't map, you don't end up with the non-ident. Yeah, the G, that's simpler than a gamma. You can use a gamma for sure. But then you will have to, remember you have to take gradients through this. So there's work on our lab actually that generalize reparametrization gradient to these distributions, so you can use that. But a simple thing to do, and that's shown to work in the other related paper that came this year, is just to map that to a softmax. Yeah, or soft plus would do too. All you want is a non-negative constraint. Yeah. Thank you.